I want to start today by asking you to do something a little weird. It's a visualization exercise, and it comes straight out of the research paper we're covering.
Okay, I'm game.
I want you to just imagine a spiral drawn on a piece of paper, a simple classic spiral.
Got it.
Now, in your mind, trace that spiral. Start from the very outside and just wind your way into the center.
Done. Easy enough.
Right. For a human, it's easy. But think about what your mind's eye just did. You didn't scan the image like a photocopier, right? Going strictly left to right, line by line.
No, of course not. You follow the path. Where you look next depends completely on where you were just looking. It follows the line.
Exactly. It's a logical progression.
We call that a causal dependency.
Yeah.
Your visual processing is being driven by the content, the shape of the line, not some, arbitrary grid you've laid on top of it.
But here's the kicker, and this is the problem we're unpacking today. That is not how most AI models see the world.
Not at all. The industry standard for these vision language models, or VLMs, uses what's called a raster-scan.
Raster-scan, so like my old TV.
Basically, imagine you're trying to read a comic book, but instead of following the speech bubbles and panels in order, you just mechanically read every single pixel from the top left corner straight to the bottom right.
So if there's a picture in the top right and a caption way down in the bottom left?
The model doesn't care. It scans row by row. It's incredibly rigid. And, that works fine for simple snapshots, like a picture of a cat on a mat.
But for a complex document.
Exactly. If you flatten a complex document, say a scientific paper with charts, sidebars, maybe a quote in the middle, into a rigid 1D sequence based purely on coordinates, you completely break the semantic relationship of the data.
You're turning a coherent layout into just word salad.
Worse than salad. You're forcing a text-reading bias left to right, top to bottom onto visual information that doesn't follow those rules.
Yeah.
You lose the entire context of why things are placed where they are.
Which brings us to our stack for today. We're looking at a paper titled DeepSeek-OCR 2, Visual Causal Flow. The researchers at DeepSeek AI are trying to solve this photocopier problem.
And their mission, really, is to build an architecture that doesn't just scan an image, but actually reads it with the same kind of logical flow that a human uses.
And they do that with a new system called DeepEncoder V2. The big claim here is that this achieves visual causal flow.
Meaning the AI decides where to look next, based on logic, not just geometry, moving from a robot scanner to a reasoning reader.
Okay, let's get into the guts of this, because when I looked at the architecture diagram, something jumped out at me that seemed, backward. They're using a language brain to solve a vision problem.
It does sound counterintuitive. To get why it's a big deal, you have to look at the status quo. Almost everyone else uses an architecture called CLIP.
CLIP is the big one, yeah. The standard vision transformer.
Right. And CLIP is fantastic at general associations, matching an image of an apple to the word apple. But it's static. It just takes a snapshot. DeepSeek-OCR 2 throws CLP out. Instead, they use a language model architecture. Specifically, Qwen2 Dan 0.5b to act as the vision encoder.
Hold on. A language model to be the eyes. How does a text generator even process pixels?
That's the brilliant part. Think about what a language model is really, really good at.
Next token prediction.
Right. It's good at understanding sequences. That B follows A, that the end of a sentence depends on the beginning. It is built for causal reasoning.
So they figured if we want an AI to read an image in a logical sequence like tracing our spiral, we should use the brain that's already an expert at sequences.
Exactly.
Yeah.
They realize that vision, at least when it comes to documents, isn't just spatial, it's temporal. It happens over time. You look at a header, then a subhead, then a paragraph. That's a sequence.
But you can't just feed a JPEG into an LLM. It expects words.
No, you can't. And this is where they have this clever dual stream mechanism. It's a two-step process. First, you have what they call visual tokens, or the prefix.
The prefix. Walk me through that.
Okay, imagine walking into a crowded party. In the first split second, you don't see specific faces. You just see the room, the layout. Bar over there, dance floor there, exit there. It's a global, all-at-once awareness.
So that's like my peripheral vision kicking in.
Exactly. DeepSeek uses a tokenizer to turn the image into these global tokens. And crucially, this part uses bidirectional attention.
Meaning everything is connected to everything else?
Yes. Every part of the image can see every other part at the same time. The top left knows what's in the bottom right. This gives the model that party layout context. But that's just the setup. The real magic is the second stream, the suffix.
So if the prefix is me seeing the room, the suffix is?
The suffix is you deciding to weave through the crowd to get a drink. It's the specific step-by-step action. After the visual tokens, the model adds what it calls learnable queries, and these queries use causal attention.
Learnable queries. That sounds abstract. What is a query here?
Think of it like a spotlight the model controls. The first query looks at all that global data and asks, okay, where's the text start? And the model focuses there. Then the next query looks at that spot and asks, given that I just read this word, where is the rest of the sentence?
So it's dynamic. It's not just sliding down the page. It's asking what comes next logically.
Yes. These queries can look back at all the fuzzy global info, the peripheral vision, and they can look at the previous queries to decide the path. It effectively decouples position from order.
There was a visualization in the paper, Figure 5, that showed this attention mask. It looked like a square grid right next to a triangle.
That's the technical drawing of what we're talking about. The square on the left is the image fully connected, everything seeing everything. That's your map. The triangle on the right is the causal flow step-by-step logic. That's your GPS road.
I like that. The map shows you where the roads are, but the GPS tells you the order to drive them in. And DeepSeek is building the GPS right into the AI's eyes.
That is a perfect analogy. And because this GPS is built on a language model architecture, it naturally speaks the same language as the final text generator.
But complexity usually means cost, more parameters, more compute. How heavy is this thing?
That's the surprise. It's incredibly efficient. They use a vision tokenizer with an 80 million parameter compressor.
80 million. In a world where we talk about 70 billion or more, 80 million sounds tiny.
It is tiny. And its job is just aggressive compression. It reduces the number of visual tokens by a factor of 16.
Why should we, or the listener, care so much about token counts?
Well, if you want fast, cheap AI, you have to. Tokens are the currency of AI. Every token costs money and time to compute. Shoving a raw 4K image into an LLM is thousands and thousands of tokens. It's slow. This model keeps the budget between 256 and 1,120 tokens per image.
1120 is the absolute max.
Yes, and that number isn't an accident. They explicitly compare themselves to Gemini 3 Pro, which has that same maximum visual token budget. They're matching the industry leader's efficiency.
My worry, though, is if you compress an image by 16 times, aren't you turning the fine print into a blur?
That's a valid concern. If you just shrunk the whole image, you'd lose all that detail. So they use a multi-crop strategy. It takes one global view of the whole image to get the layout. Then it can take up to 6 high-res local crops of specific areas.
So it zooms in where it needs to.
Exactly. And because of that causal query system, our GPS, it knows how to stitch those zoomed-in crops back together in the right logical order.
I want to shift to how this thing actually learns. The paper outlines a three-stage training pipeline. It sounds very structured.
It is. Think it like sending a kid to school.
Yeah.
Stage 1 is encoder pre-training. This is kindergarten,
Learning the alphabet.
basically. Learning to see shapes and features. They're just teaching the vision encoder to extract features from images. This is a line. This is a curve.
And after kindergarten,
Stage 2 is query enhancement, middle school. They freeze the tokenizer so the eyes are set, but they train the encoder and decoder together. This is where the model learns to use those causal queries to reorder information.
this is like learning grammar, learning that a header comes before a paragraph.
Correct. And finally, stage 3, decoder specialization. This is grad school. They freeze the whole vision system. Now they just train the final LLM decoder, the part that actually writes the text, to interpret those reordered tokens perfectly.
It's very compartmentalized. But I noticed something about the data they use. They didn't just throw a million random PDFs at it.
No, the data mix was highly engineered. For their OCR 1.0 data, they refined the sampling to a 3:1:1 ratio for text, formulas, and tables.
Wait, 3.1.1, so they significantly oversampled formulas and tables. Why do that?
Because formulas and tables are the absolute boss battles for raster-scan models. Think about a complex math formula. It has superscripts, subscripts, fractions. It's vertical. You can't read a fraction left to right.
Right, if you scan it across, you get the numerator, then some other text, and the denominator. Total nonsense.
Exactly. By forcing the model to look at a disproportionate amount of tables and formulas, they forced it to get really good at that nonlinear, spiral-like reading we started with.
So they built the car, they tuned the engine. Does it actually drive? Let's talk results on the OmniDoc bench.
They did. And the headline number is 91.09% overall performance. That's a 3.73% gain over the previous version.
Now I can hear some people shrugging. 3%, that sounds like a rounding error.
In the OCR world, where you're fighting for every fraction of a point, 3.7% is a solid leap. But that percentage isn't the most interesting part. The real story is in a metric called reorder.
Or order.
Reading order, yes. They measured the edit distance for reading order, basically asking, even if you got the words right, did you put them in the correct sequence? The error rate there dropped from 0.085 to 0.057.
That's a huge drop in errors. That's like a 35% improvement in just knowing how to read the page.
It proves their whole hypothesis.
Yeah.
The model isn't just recognizing characters better, it understands the document structure. That's the causal flow in action.
And how did it stack up against Gemini 3 Pro?
Gemini 3 Pro had an edit distance of 0.115. DeepSeek-OCR 2 was at 0.100. So on the metric of, did I read this in the right order, it actually outperformed a much larger model using a similar token budget.
That is significant. And they also included some stats from their own production logs, the real-world test.
This is where a lot of academic papers fall apart. They work in the lab but fail in the wild. But they looked at the repetition rate.
Oh, the repetition loop. I hate that. When the AI just starts printing the same thing over and over.
Or it reads the page header on every single line. It's a hallucination. In their production logs, the repetition rate dropped from 6.25% to 4.17.
Which sounds small, but if you're a developer feeding 1 million PDFs into this thing to train another AI, a 2% drop in junk data is huge.
It's massive. Less hallucination means cleaner data, which means your downstream models are smarter.
However, we have to look at the losses. And in Table 3 of the paper, there's a glaring weak spot.
Oh, it jumped right out of me too. Newspapers.
It failed pretty hard on newspapers. Why?
The edit distance was way higher. The researchers are pretty transparent about it. And it boils down to two things: resolution and history.
Okay, let's start with resolution.
Newspapers are what they call text super rich.
Mm-hmm.
Tiny font, narrow columns. Remember our token limit? 1,120 tokens.
Right.
For a dense newspaper page, 1,120 tokens just might not be enough resolution to capture every character. The compression is too aggressive.
So it just kind of blurs out.
Basically.
Yeah.
And the second reason is data scarcity. They admitted their training set only had about 250,000 newspaper samples.
250,000 sounds like a lot.
In deep learning, it's a drop in the bucket. They simply didn't teach it enough about how newspapers work, which is ironic, isn't it?
How so?
Newspapers are basically the archive of the last 200 years of human history. If we want AI to digitize our history, failing on newspapers is a big deal.
That's a great point. It suggests that general vision isn't enough. You need specific cultural training on how we used to lay out information.
It shows that even with this fancy causal flow, the model is still bound by what it has seen.
Let's zoom out. The paper wraps up with a discussion section that gets pretty philosophical. They use the phrase genuine 2D reasoning.
This is the part that gets me really excited. They're proposing a paradigm shift. They're suggesting that maybe genuine 2D reasoning is best achieved by cascading two 1D causal reasoners.
Okay, cascading 1D reasoners. Let's unpack that.
So reasoner 1 is the encoder. It looks at the 2D mess of the world and creates a 1D logical path. Look here, then here, then here.
That's our causal flow.
Right. And reasoner 2 is the decoder. It takes that logical path and then reasons about the content textually.
So instead of trying to understand the whole 2D picture at once, you serialize it. You turn space into time.
You turn a map into a set of directions. Directions are 1D, they're a sequence, but they explain the 2D space perfectly.
Which leads to that other concept they teased, native multimodality, a unified omnimodal encoder.
This is the logical next step.
The idea that since the brain of this thing is just a language model, it could do more than just see.
Right. Think about it. The encoder is just quint-to-text brain. It processes queries. Right now, those are visual queries looking for the next patch of pixels. But the architecture is generic. You could theoretically plug in audio queries.
Wait, so the same brain could listen to a podcast?
Theoretically, yes. Instead of looking for where is the next word in the image, it would look for where is the next sound in the waveform. The logic of what comes next is universal.
So you wouldn't need a separate model for hearing and a separate one for seeing?
No. You would just have different learnable queries for different senses. The underlying brain, the encoder, stays the same. It processes everything as a language, as a sequence of causal events.
That is a wild thought. We think of vision as spatial all at once, and language as temporal over time. But this paper suggests if you treat vision as temporal, you solve the problem better.
And the success of the R order metric proves they're onto something. By treating the image as a story to be read, not a landscape to be surveyed, they got better results.
So for the listener right now, this means better OCO tools are coming. Fewer formatting errors when you copy-paste from a PDF.
Correct. But if you are watching the field of AI, This is a signal that the specialized modules era might be ending. We're seeing a convergence where the architecture language model is just eating everything else. It's becoming the universal structure for reasoning.
DeepSeek-OCR 2 isn't just a better reader, it's a proof of concept for a universal perceiver.
I would agree with that. It really validates that the gap between seeing and reading is much smaller than we thought.
I want to leave you with a final thought to mull over. If we can solve visual logic using these 1D causal structures, just like language, does that imply that human consciousness, which we experience as a stream of thought, is actually just a really good 1D serializer of a complex, multidimensional world? Are we all just tracing spirals in our heads to make sense of the chaos?
That is a deep philosophical rabbit hole to end on.
Yeah.
But you might not be far off.
That's what we do here. We start with pixels and end with existential crises. Thank you for guiding us through the causal flow today.
Always a pleasure.
And thank you for listening. Keep tracing those spirals, and we'll catch you on the next deep dive.